Let's continue with the Chapter 5 test review, worksheet number 1. This is the back page, number 3. This is this is an old AP problem from 1994, number 4. A particle moves along the x-axis so that at any time where t is greater than 0, its velocity is given by this v of t function. So this is a particle motion problem where positive velocity means this particle is moving to the right. Negative velocity would mean that the particle is moving to the left. Write an expression for the acceleration of the particle. So acceleration would be the derivative of this velocity function. So let's see how we can find the derivative of this. All right, notice that you have t, which is a variable, and you have ln of t, which is going to be a separate function. So if we want to find the derivative that involves two separate functions that are being multiplied together, and we're going to have to go through product rule. So we have to be careful here. Go through product rule, and then the t will just become 1. So first we go through product rule, so f prime g plus f g prime. So f prime is the 1 times g plus the f function times g prime. So the derivative for ln of t is 1 over t, and then this variable t will turn into a negative 1. So we clean this up a little bit. Natural log of t plus the t over t becomes 1. So natural log of t plus t minus 1. The 1's cancel out, leaving us with just natural log of t. So our acceleration function is simply natural log of t. Okay, part B, for what values is the particle moving to the right? So we can find critical points by figuring out where velocity is 0, and then from there we can test the intervals to the left and to the right. Now we're given the velocity function to begin with, so we can, to find the critical points, let's just set our velocity function equal to 0, because to figure out where the graph, or where this particle is moving to the right, we first need to determine to see, is the particle even, where's it stopping? All right, where's it stopping? Where's the critical point? And then we can test the intervals to see when it's moving to the right. So we set our velocity equal to 0. So our velocity is t, natural log of t minus 1. Set that equal to 0. We can factor out the t. So t times ln of t minus 1. Set ln of t minus 1 equal to 0. Set t equal to 0. Natural log of t equal to 0. Now remember, natural log of t, we can think of that as log base e of t, right? Natural log is simply log base e. And if I solve for, if I convert this to exponential form, I get e to the first power is equal to t. So my critical point is at t equals e and at t equals 0. Now 0 is already going to be our starting point, because here they've already determined that this particle is moving to the right of 0. So we'll think of 0 as our starting point, and our critical point is at e. So we know the graph is going to, so we just need to test two values here, between 0 and e, and between e to infinity. So e is roughly 2.7, so let's plug 1 into the derivative, into the velocity function. So if I plug 1 into the velocity function, I'll get positive times, let's see, this is natural log of 1, which is 0. 0 minus 1 is negative. So I have positive and negative, which gives me a negative. So I know that this particle is moving to the left, right? Negative velocity means particle is moving to the left. Now to the right of e, let's choose maybe 4 or 5. Natural log of 4 will produce a y value that is greater than 1. So 1 minus, or greater than 1 minus 1 will be a positive, times a positive, which is positive. So we know this particle is going to move to the right, to the so go to the left, stop at e, and move to the right. So particle will be moving to the right. That's what part B is asking for. For what value of t is the particle moving to the right? Moving to the right when t is greater, when the velocity moving to the right for t values from e to infinity, and the reason is because velocity is greater than 0, is positive. Okay, part C, what is the minimum velocity of the particle? Now let's think about what this is asking. If we ask for the minimum position of the particle, the minimum position will occur when the velocity changes from a negative to a positive, right? So E is the minimum position, but it's asking for the minimum velocity. So minimum velocity, we have to look at the rate of change further down. Minimum position is when velocity changes from negative to positive. So minimum velocity would be where acceleration changes from negative to positive. So that's exactly what we need to find. So we need to find when minimum velocity occurs when v prime, or acceleration, changes from a negative to positive. So you can think of it as finding critical points, finding POI, because that is where we can think of acceleration, is critical points for acceleration. So we can set our acceleration equal to 0. So set natural log of t equal to 0. To convert this to exponential form, I'm going to convert this, rewrite this as log base e of t is equal to 0. And then I have e to the 0 is equal to t, so t is equal to 1, because anything raised to the 0 is simply 1. So I have a critical point at 1. My starting point is at 0. Let's test the acceleration in this interval. So if I plug, let's say, 0.1 or 1/2, natural log of 1/2 will give me a negative value, because I know that based off of what we know with a natural log graph, the graph will be below the x-axis between 0 and 1. To the right of 1, we know that natural log graph will rise above the x-axis, so it will be a positive acceleration. So we see that there's a minimum velocity will occur because acceleration changes from negative to positive at t equals 1. Okay, number 4, find the derivative of our equation here, y ln of x plus y squared is equal to 0. Now, if we want to find the derivative, a couple of things here. We see the y's are mixed in with the x's, so we have to go through implicit differentiation. And also, we have y and ln of x. We have to find the product, the derivative of these expressions, but they're in a form where they're multiplied together, so you have to go through the product rule. So a couple of things that we're going to have to incorporate when we find the derivative is first implicit differentiation, and then also product rule. All right, so implicit differentiation means that each time we find the derivative that involves y, we have to attach a dy dx. And product rule, we know f prime g plus f g prime. So let's look at here. We have y ln of x. We have two separate functions being multiplied together. We have to go through product rule. So f prime g, so the derivative of y is 1, but because we're involving y's derivative, we have dy dx. That's my f prime. G is my original ln of x, plus f g prime, so my g function, f function is back to y, and the derivative of ln of x is 1 over x. So this is the product rule for this first portion, y ln of x. Let's move on to y squared. Y squared is simply a variable by itself. We can go through power rule, so y squared becomes 2y, but again, we're involving y's derivative. We have to attach dy dx equal to 0. So now we just have to try to get dy dx by itself. I'm going to move the y negative y over x to the right side. Factor out the dy over dx for the natural log of x and for the y. And then once I'm here, I'm going to divide both sides by natural log of x plus 2y. Complex fraction here, I can multiply top and bottom by x, or I can just move this x down to this denominator to share with this natural log of x plus 2y. So here we have our derivative for our equation, applying implicit differentiation and product rule. Okay, number 5, find dy dx if y is equal to the cube root of 2 plus 5x cubed to the x. I'm going to rewrite this, so make it a little bit easier to see what we need to do. I'm going to rewrite this as rational exponents, 2 plus 5x cubed to the x over 3. Now, if we want to find the derivative of a variable raised to another variable, we don't have a rule for this. So we have to find a way to get that exponential variable down. So the way we can do that is we can use log properties, but in order to use log properties, we have to have a log expression involved in this expression. So we have no logs in the problem, but we can introduce logs by using log differentiation. So let's take the natural log of both sides. So when we do that, now the right side allows us now to use power property for logs by bringing this exponent x over 3 down to the front. So now we can think about our derivative process. ln of y, we have y mixed in. It's within a function now. It's not by itself. So we have to go through implicit differentiation. ln of y becomes 1 over y times dy dx. And here we have x over 3 as a separate function from natural log of 2 plus 5x cubed. So again, we have to go through product rule. So f prime g, the derivative for 1/3 x is simply 1/3. So f prime g plus f times g prime. So the derivative for ln of u is simply u prime over u. The u prime is the 15x squared. The u is the 2 plus 5x squared. And then we can clean this up a little bit. And then once we do that, we can bring the y over to the right side. Once we bring the y over to the right side, then replace y with our original equation. So we can express our derivative in terms of one variable x.